Today, we will be comparing two different control strategies to make our robot travel in a straight line and pivot a certain degree. In the first strategy, we will only use the wheel encoder counts as the feedback for the control, while in the second strategy, we will be combining wheel encoder information with the yaw angle returned by the IMU. In the first strategy, using only wheel encoder information, we assume that if the robot is traveling in a straight line, then the left and right wheel encoder counts should remain the same. Thus, we consider the difference between the left and right encoder counts as an error and use a PID controller to actively drive this error to zero. The output of this PID controller is used to modulate the difference between the left and the right wheel speed. In the second strategy, combining the IMU data, we can design another PID controller based on the difference between the starting heading angle and the current heading angle, and we add that to the previously mentioned PID controller based on wheel encoder count. Therefore, the wheel speed difference across the left and right is the summation of two controllers' output, and it should be more robust than using just the encoder information. With regard to pivoting a certain degree, if we only rely on the encoder counts, we could assume a certain center of rotation and calculate how much the wheel would travel if the robot is spinning in place by a certain degree. And of course, in this case, we assume that there's no slipping of the wheels. Then we could convert this distance to be traveled by the wheel to the encoder counts and stop the wheels when the encoder counts reach the desired number. In the second control strategy using the IMU, we could treat the difference between the desired heading angle and the current heading angle as an error, and use another PID controller to drive this error to zero, such that the robot would pivot by the desired amount. The second strategy should produce a much more accurate result than the first strategy, since it has access to the yaw angles. Next, we will do a demonstration first with only the encoder information as the controller's feedback. In this demo, the robot will try to traverse a square trajectory, and each side of the square is 40 centimeters long. As we can see, with only the encoder information, the robot can still travel relatively straight, but the turning angle is vastly off, such that the localization error by the end of the run is quite big. Next, we will see the demonstration with the IMU data incorporated. As we can see, the robot almost completed a perfect square, and therefore the second control strategy with the IMU data incorporated is much more accurate and robust than using only the encoder information.